Hello guys. Welcome back to the continuation video on black holes. This is Tridenour Science. First of all, if you have not watched the part 1 video of black holes, then please go and watch it. Link is in the description, and also in the I button at the top. The part 1 video is the prerequisite of this part 2 video on black holes. In this video, we discuss about some different types of black holes and their features. We will also get to know about what is the black hole information paradox, and some of the concrete evidences on the existence of black holes and some other interesting stuff. So guys, watch the video until the end to know more about the black holes. Then let's dive right in. The scientists have discovered 4 main types of black holes in the universe. The most common type are the stellar black holes, which are formed due to the gravitational collapse of huge stars. A typical stellar black hole has a mass between 3 to 10 solar masses. These stellar ones grow to form intermediate black holes by engulfing large mass from the gases, interstellar dust, or even from other stars. The intermediate ones have a mass of around 100 to 100,000 times the mass of our Sun. Definitely much larger than the stellar ones. It is also possible that the stellar black holes can merge together and form what are called the supermassive black holes. This process of merging is believed to be important in the early growth of the supermassive black holes. The mass of the supermassive ones range from mind-blowing millions to billions of times the solar mass. The 4th type of black holes are tiny and hypothetical. They are called as the micro black holes or the quantum mechanical black holes, for which quantum mechanical effects play an important role. The concept that black holes may exist that are smaller than stellar mass was introduced in 1971 by Professor Stephen Hawking. These quantum primordial black holes are possible to have been created in the early environments after the Big Bang, where the densities were very high. Some hypotheses involving additional space dimensions predict that micro black holes could be formed at energies as low as the tera-electron-volt range, which are available in particle accelerators such as the Large Hadron Collider. But due to the emission of Hawking radiation, these black holes evaporate instantly, as the amount of radiation emitted is indirectly proportional to the mass of a black hole. In principle, these black holes can have any mass equal to or above about 22 micrograms, which is called as the Planck mass. Today it is believed that almost all of the large galaxies have a centrally located supermassive black hole, forming quasars and finally the active galactic nucleus. These active galactic nucleuses warm up the gases and dust and pushes it away, thereby fueling the process of star formation. Our Milky Way galaxy also has a centrally located black hole known as the Sagittarius A star, but this black hole currently is inactive, that is, it is not feeding on the mass around it. This black hole certainly gets active when the collision course of Milky Way and Andromeda galaxy begins after 4 to 5 billion years from now. According to the no-hair theorem, a black hole eventually attains the stable state with only 3 independent physical properties. The mass, charge, and the angular momentum are the only 3 parameters which feature the difference between the different black holes. If the conjecture is true, any 2 black holes that share the same values for these properties, or parameters, are indistinguishable from one another. But the degree to which the conjecture is true for real black holes under the laws of modern physics, is currently an unsolved problem. Because a black hole has only a few internal parameters, most of the information about the matter that falls into a black hole is lost. Regardless of the type of matter which goes into a black hole, it appears that only information concerning the total mass, charge, and angular momentum are conserved. This was not a problem because it was believed that the information is lost only to the outside world, but it exists inside the black hole. But when Professor Stephen Hawking discovered the Hawking radiation, in theory, which says that the black holes eventually evaporate by giving out the Hawking radiation, this puzzled the physicists, as they thought that the gravitational and the electromagnetic fields of the black holes give out so little information about the falling objects, and now this Hawking radiation does not appear to carry any additional information about the matter that formed the black hole. This meant that the information appears to be gone forever. This behavior is so puzzling that it has been called the black hole information loss paradox. The appearance of singularities in general relativity is commonly perceived as signaling the breakdown of the theory. This breakdown, however, is expected, as it occurs in a situation where quantum effects should describe these actions, due to the extremely high density and therefore particle interactions. The study of black holes and their other phenomenons are very crucial for the advancements in science and technology, as they lead us into the next generation of exploration and better understanding of the universe. To date, it has not been possible to combine quantum and gravitational effects into a single theory, although there exist attempts to formulate such a theory of quantum gravity. It is believed that such a unified theory will become the theory of everything, explaining everything in the universe. The existence of these black holes can be inferred by observing different phenomenons that are created by them. Some of the concrete evidence for the existence of black holes are the gravitational lensing. This phenomenon distorts the path of the light around large and heavy objects, such as a black hole. On the 14th of September 2015, the LIGO Gravitational Wave Observatory made the first ever successful direct observation of gravitational waves. The signal was consistent with theoretical predictions for the gravitational waves produced by the merging of two black holes. The proper motions of stars near the center of our own Milky Way galaxy provide strong observational evidence that these stars are orbiting a supermassive black hole. The Event Horizon Telescope is an active program that directly observes the immediate environment of the event horizon of black holes, such as the black hole at the center of the Milky Way. In April 2017, Event Horizon Telescope began observation of the black hole in the center of Messier 87 galaxy. In all, 8 radio observatories on 6 mountains and 4 continents observed the galaxy in Virgo on and off for 10 days to provide the data yielding the image of a black hole. After 2 years of data processing, on the 10th of April 2019, Event Horizon Telescope released the first direct image of a black hole, specifically the supermassive black hole that lies in the center of the Messier 87 galaxy. Black holes are a marvelous wonders of the universe, as much as they are such a monstrous entity of the cosmos. We human beings as a civilization altogether should learn from the black holes and suck in all the knowledge around us, and eventually grow together by merging or collaborating for the betterment of the mankind. There is so much more for us to learn and become better. So, be curious and imaginative. Thank you for sticking around. And we will be coming back with more fascinating things in the universe for you to learn and be amazed. So stay tuned. Please like and share the video. And subscribe to our YouTube channel to get notified whenever a new video drops. Please follow us on Instagram and Twitter. Up to then, goodbye.